Okay, we're going to look at a few more details of how hash tables work in this video. Now, hash tables are a set, and so they support the same type of operations on a set. So we're going to do an insertion, and when we do an insert, we could think of the insert as taking both the key and the data, right? We use the key to calculate the index in the hash table, and then we insert the data there. But like for primitive types, the key and the data is the same, so we don't necessarily need this differentiation. And so when we do an insert, we add the data to the hash table using the key. When we do a search, we check to see if data with the corresponding key is in the hash table. When we do a remove, we remove the data with the corresponding key if it's in the hash table. So basically the same things we want to do as in a set. A hash table is going to have an array that holds the data. I'm often just going to synonymously call that table the hash table, since it is an array. It needs to be an array because when we calculate a position to hold the data, we need to be able to calculate that position efficiently. Like, we don't want our hash table to actually be a linked list, because there's no way to just jump to a position in a linked list, right? The only thing that allows us to jump into the middle of a data structure and know exactly where a position is an array. And so this has to be an array. And then this array is going to be set up to be some size that we know, some big size that's a lot bigger than the number of items we're going to insert into it. And then we also have what's called a hash function. And the hash function that we've been considering so far is modulo 10, but that's not a very good hash function. And we're never going to use that in real life. It's just helpful for making slides. But the hash function takes the key and turns it into an index somewhere in this array, right? Somewhere in this table array that's holding all of our data. Oftentimes, this hash table array, we call each entry in it a bucket. And a bucket can be empty, meaning it has no data, or it can hold one or more items of data. And it's important that our table have enough buckets, and that those buckets can hold enough data that however much data you expect to be in the hash table, you should be able to hold that much data in the array. So there's an element of hash table design where you kind of have to do a little guesswork, and you kind of are hoping you can figure out about the right size array to allocate up front. But if you can't, it's not a big deal. We can always resize this array later to accommodate the amount of data we really have, but if we can kind of know up front, that's good. So for example, if we expect our hash table is going to hold 10 integers, then we would need this table to have at least length 10. In fact, we probably wanted to have at least length 20. Roughly double the number of entries is usually kind of a rough back of the envelope guess for how big you want your array to be. Roughly double, maybe more. Okay, the hash function has several properties that need to be met. The hash function is going to map a key to an index in the table. Okay, this function needs to be fast. Modulo 10 is fast. Any other basic math equation you might write out with a few terms, that's going to be fast. But we don't want to do anything that would take a long time. Like, we definitely don't want to like search the table for a free position, because that would be order n again, right? This has to be order 1, which means it needs to take the key, it needs to do something tricky to it to come up with an index. And then when we do that, that index, it's kind of obvious to say, but whatever indices the hash function produces, it should be able to produce any valid location in this table, right? For this table of length 10, my hash function should be able to produce any value from 0 to 9, which modulo 10 can do. And then the other thing I want it to do is to spread the data fairly randomly across the table. Because if I send in the same, very related numbers, I don't want them going to the same spot, because if they go to the same spot, they collide. And then I can't store as much information in my table. So I need it, so the way I can force an index to be in range is with modulo, right? However big the size of the table is, the last step of my hash function is almost always going to be a modulo with the size of the table. And that's going to generate a number from 0 to size minus 1, always. And then a little trick we can use is if we always make our table a prime number in length, then dividing by a prime number, it's kind of well known, but that does a good job of spreading data from 0 to 1 to the prime minus 1. Because since primes don't have many factors themselves, when you divide numbers by primes, there aren't many common factors. So there aren't going to be as many patterns, and they're going to do a better job of spreading your data across your table. But we're also going to need to come back to this point, because it's not quite that simple, right? It's not just so simple as you need to do a modulo by a prime number, and then voila, you have a great hash function. It's a little more complicated than that. But these are some of the basic essential desires, right? We should be able to use the whole table, and we should try to spread our items that we're storing in the table throughout the table, so that we use the space we've allocated efficiently. Okay, so collisions, I've mentioned this a few times already in the videos. Collisions occur when multiple keys map to the same index. So suppose I'm using mod 10, and I need to insert both 24 and 144 into my table. But I've already put 14 in my table. What do? There's nowhere for it to go. That's a collision. These are all collisions. I only have one entry to hold 3 data. This is really vexing because I actually have a lot of other empty spots in my table. It's just that my hash function's too dumb to stick them there. Like I wish 24 was mapping to 6, and I wish 144 was mapping to 0, but it's not. So collisions happen when multiple data items get mapped to the same index, and you already have data stored there. And so we obviously want to minimize collisions. And one way we can minimize collisions is by having a better hash function that does a better job spreading the data. Another way we can minimize collisions is by having a much bigger table, because the bigger the table, the smaller the odds that 2 things map to the same index. And then there are more, designing that better hash function can be a very effective strategy. But it's, designing good hash functions isn't a simple thing, and it's not always guaranteed to work. And so we'll see some other techniques for dealing with collisions in a more systematic way. Okay, so in summary, a hash table is a way of implementing a set. It supports operations like insert, remove, and find. The key pieces of a hash table are the hash table array. Each entry in that hash table array is called a bucket. And this array needs to be big enough to hold all the data we want to hold in our set. And then we also need a hash function that maps a key to an index in the table. And a good hash function is going to minimize collisions and use the full range of entries in the table so that we can store as much data as possible.